Greetings one and all. Welcome to the third lesson from chapter 9 on constant acceleration. So far we've seen displacement time graphs, we've seen velocity time graphs, and now we're going to piece together the ideas from velocity time graphs to begin to derive the SUVAT formulae. And what SUVAT formulae are, it's the name, the informal name for the formulas for working out, in no particular order, displacement, initial velocity, final velocity, constant acceleration, and time of motion for any object which can be modelled as moving with constant acceleration. So we're going to begin to prove some of those formulas today, and we'll finish off proving the rest of them next lesson. So before we get into the main portion of that, there are some warm-up questions for you to get you started and thinking. So here they are. Try them now on your own, on pen and paper, or in your notes, and press play only when you've made your best effort to do them independently. So once you've done them independently, unpause and press play to see how your solutions check against mine. So assuming you've had a go at these already, let's have a look now together at the solution to question 1. So here we have a particle moving in a straight line from a time t equals 0 seconds to time t equals 4 seconds. Its velocity increases at a constant rate from 10 meters per second to 15 meters per second. Sketch a velocity time graph to illustrate the motion of the particle. Now, here, what hopefully you've noticed, well, I don't say you can't notice really, is I've actually sketched in advance the axes. And so all I need to do now is to label the axes. And so time is always the independent variable in these situations. So we put time on the horizontal axis, and up here on the vertical axis is velocity. And now we're told that its velocity increases at a constant rate. Now this means the acceleration is constant and the gradient of the line will be constant. It'll be a straight line graph. So it starts off at 10 meters per second, and it's going to increase its speed. It's going to accelerate to 15 meters per second. So starting here, it's going to accelerate like so. Okay, so its final speed we can label is 15 meters per second. In fact, what I'll do here, I'll include the units as well. So velocity here is in meters per second. Likewise, time is in seconds. And it says here as well that it takes it 4 seconds to get from 10 to 15 meters per second. So on the horizontal axis, I can also label the time here as being 4. And so I've included all the information I need, and so that finishes off the sketch for question 1. So we can now have a look and think about question 2. Question 2, it says use your graph in question 1, or otherwise, to find the acceleration of the particle. So we need to remind ourselves of the graph we just sketched in question 1, so here it is. So we need to think about how to work out the acceleration of the particle. So going back to first principles, what does acceleration mean? So acceleration is just simply the rate of change of velocity. So that's what it actually means. It's the rate of change of velocity. And so in other words, it's the velocity divided by the time in which the velocity's had to make that change. So it's the change in velocity divided by the time taken for that change. And we can use this graph to calculate this for us. So the acceleration, I'm going to call that A, because that is the standard letter for acceleration. So the change in velocity, let's just label this a bit more in fact. So if we go from this point to that point, let's just consider the length of this line. Okay, if I just change the colour of that line as well, just to make it clear that it's a different type of line to what we had before, then from there to there, we can see that's 4 seconds. And likewise as well, in terms of the change in velocity, in terms of how far the graph has gone up, how far this line's gone up, if I change colour there, it started at 10, it's gone up to 15, so this change here is 5. So we can now input this into our formula for acceleration. So the change in velocity is 5 meters per second. And the time taken for that change, it moved from 10 to 15 meters per second in a time of 4 seconds. So 5 meters per second divided by 4 seconds, that gives us, using decimals, 5 divided by 4, which is 1.25 meters per second, which is actually meters per second squared, which we write like this, ms to the power minus 2. Question 3 is also asking us about question 1 again. So calculate the final displacement of the particle in question 1. So again, just remind us of the graph from question 1. How do we work out the displacement if we have a velocity time graph? Well, we need to remember a crucial concept here, and this goes on later on for this lesson as well, that displacement is given by the area under a velocity time graph. So that is a crucial concept which we need to explore a bit further today as well. So this is absolutely key for working this out. So the total displacement will be the total area underneath this red line, between the red line and the time axis. And so what we need to do here is just to calculate this area. I'm just going to very roughly shade in this green colour. Okay, so we're after all of this area. So hopefully you can remember how to work out the area of a trapezium, and if not, you could, dare I say, get away with thinking of this as a triangle stacked on top of a rectangle. But I'm going to assume we know how to work out the area of a trapezium. So the area here, the displacement in other words, is going to be half of the two parallel sides of this added together. And so this side here is 10. The height of this side here, in terms of the vertical scale, the velocity scale, is 15. That goes from 0 to 15. So it's a half of 10 plus 15. The average of 10 plus 15, if you like, multiplied by the width. You can see here this has a width of 4. And so if you were to work this out on your calculator or otherwise, you should find that you get 50 meters for that one. So therefore, the displacement during this journey is 50 meters. Finally, for warm-up, question 4, the object described in question 1 is a cyclist modelled as a particle. It now says to write down an assumption that can be made when objects are modelled as particles. Okay, so when we model objects as particles, we can make a few assumptions. We can assume that there's no air resistance, because if it's just a point particle, there's nowhere for the wind to actually blow at if it's just a singular point. Also as well, we can consider the mass to be centred at one point. And that's it for the warm-up. So let's now have a look, without further ado, at the main bit of this lesson. So the constant acceleration formulae, part 1. So we're going to have a talk about how we can actually arrive from first principles at what these formulae actually are. So, without further ado, let's go forward. So we have a standard set of letters which are used for the motion of an object in a straight line with constant acceleration. So we refer to this set informally as SUVAT. So I'm just going to give you a quick rundown of what the S, U, V, A and T mean. Some of them you can guess, a couple of them aren't maybe so obvious. Okay, so first of all, the S. Now this to me isn't particularly obvious. S, you might be thinking, well, maybe that's speed. S is speed, yeah? But the thing is, S is also a unit of time. S can stand for seconds. In this case, S, in terms of SUVAT, actually stands for displacement. So it stands for the measure of how far away the object ends up relative to where it started from. U, again, might not be too obvious. U stands for the initial velocity. V stands for the final velocity. So just think of U as being one letter before V. So U is what it started at, V is where it's ended up at in terms of velocity. A is the acceleration, and I'm putting in brackets modelled as constant. So the SUVAT formulae only apply to situations where the acceleration is constant. So the question will almost always mention about the acceleration being constant. If it mentions constant acceleration, be thinking SUVAT. T is more guessable. T stands for time. We can also add these to a diagram as well if we wish. So we've got an object here on the left in one frame of reference, and on the right it's at a later time where it's undergone a change of velocity. So we can label on these letters to give a bit more context to what we may be talking about from question to question. So first of all, just to make it clear, the left circle is the initial position, the right hand circle denotes the final position after t seconds. So I've underlined t in red in the SUVAT, just as I've underlined t here in red, so you can see here that the t stands for time in seconds. S is the displacement, so you can see here this blue arrow, which is a measure of the direct distance from the initial position to the start position. So S is the displacement. We could label on U as well, which I'm doing in purple. So U is the initial velocity. So often it's given just as an arrow, and the direction of the arrow denotes the direction of the velocity. Remember, velocity is a vector, has a size and also a direction. V, the final velocity, I've done here in green. So the arrow for V is longer than the arrow for U. That would typically denote that V has a larger magnitude than U. In other words, we can assume here, if we assume right to be the positive direction, that the object has undergone a positive acceleration. The magnitude of the velocity has increased from a smallish u to a largish v. So again, v is given as an arrow. Acceleration, again, is a vector, and this is often given using two arrowheads. Okay, so one arrowhead here, one arrowhead there. So the acceleration I've put in between u and v, just to make it clear that the acceleration is going on all the time in between when the speed is u, sorry, the velocity is u, and when the velocity is v. Even more than that, we can use the letters to label a velocity time graph representing the motion of a particle moving in a straight line under constant acceleration a. So here are the axes. And just to make note, because the acceleration is constant and non-zero, just to go back to the previous lessons, the graph will be a straight line with a non-zero gradient. So generically, it looks something like this. So label time on the horizontal axis, velocity on the vertical, and that red straight line is showing us a constant acceleration. We can now label on the letters like I've mentioned. So u is the initial velocity, that's the speed it starts from. V is the final velocity, that's the velocity it reaches at the end of the motion as described. We can also label in t for the duration of the motion, in other words, the time of motion. So if this is 0 and that's t, then t will just be simply the time during which the motion has occurred. So if we label on here what we know, so from 0 to t, that's a length of t horizontally, and if u is increased from u to v, then the change in that will be v minus u. So this height, as it were, is final velocity subtract initial velocity. And like I've mentioned before, a key concept with velocity time graphs is that the area underneath the graph will tell us the displacement during the motion. And so we could also work out the area under the graph, which I'm going to colour in here. That yellow area would tell us the displacement. So on those notes, let's see if we can calculate, in terms of these letters, some formulae for both the acceleration and the displacement. So, first off, the gradient. Gradient is the change in the vertical divided by the change in the horizontal. So in our case, it's the change in velocity divided by time. So the gradient of a VT graph tells us the change in velocity divided by time, which is the rate of change of velocity, which is the acceleration. And so the gradient, when we work it out, that's going to be telling us the acceleration. The gradient of any velocity time graph tells us the acceleration. Meanwhile, like I mentioned before, the area under the graph, that's going to be telling us the displacement. So let's work out the gradient. So the gradient, which is the acceleration, is the change in y, the y-axis, the v-axis in this case, which is v minus u, divided by the change in the horizontal axis, which we can see here is t. So therefore, A equals v minus u divided by t. That's the first SUVAT equation we've proven from first principles. We're now going to do the same using this idea of the area under the graph. So this is going to give us the displacement. The unit for displacement, the symbol, is S. So how do we work out the area of this? Well, as you can see here, typically it's going to be a trapezium. So to work out the area of a trapezium, we do half of the sum of the two parallel sides. So the first parallel side is this one. So it goes from 0 up to u, and so that's u. This one here, it goes from 0 all the way up to v, so that's v. And so half brackets u plus v, that's the average of these two parallel sides. We then multiply that by the width of a trapezium if it's laid flat. Sometimes it might be the height if it's stood the other way up. So it's going to be multiplied by t. So the displacement equals half brackets u plus v, close brackets t. In other words, the area equals this formula adapted for a trapezium. So that's how we work out displacement. That is the second SUVAT formula. There is another 3, but that's going to wait until next time. And so we've now got these two formulas involving how to work out the acceleration if we know v, u and t, and again how to work out s, again if we know u, v and t. Now let's have a look at some worked examples applying these ideas and putting them all together. So worked example 1, we have a cyclist travelling along a straight road. She accelerates at a constant rate from a velocity of 4 meters per second to a velocity of 7.5 meters per second in 40 seconds. Find the distance she travels in these 40 seconds and her acceleration in these 40 seconds. So let's just remind ourselves of what we derived from earlier. So we know now that A equals v minus u over t, and we know that s equals half of u plus v multiplied by t. So I'm just going to put that into a little box because that is something we can wheel out time and time again to help us. So part A. So it's a straight road, okay, so the direction is obvious. So in our case we can take the distance to be one and the same as the displacement. Okay, she's not travelling in a circular path or a curved path, she's not going back on herself, it's not a complicated thing she's doing. So we can assume here the displacement is the same as the distance. So the distance she travels, s, is going to be half u plus v over t. So let's see if we have enough information to do this. So u stands for initial velocity. Are we told what that is? We are. She accelerates at a constant rate from a velocity. So from means where it starts. She starts off going 4 meters per second. She ends up going at a velocity of 7.5. So that's our v. How long does it take her? We're told it takes her 40 seconds. So the time frame is 40 seconds. So now all we need to do is just plug in these values and we've got it. So it's half, brackets, 4 plus 7.5, close brackets, multiplied by 40. So all we need to do now is to get the calculator, which you know very much how to use, plug in those values, and you're sorted. So I'm going to do the same as what I'm suggesting you do. So we've got 1/2, close brackets, 4 plus 7.5, close brackets, multiplied by 40, and we get 230. And so she's travelled 230 meters. We can now think about part B. So part B says what's her acceleration in these 40 seconds? Well, now we can use this formula here. A equals v minus u over t. So v is 7.5, u is 4, and t is 40. So again, if we just plug this in, I'm colour coding because I'm addicted to it, don't know why. So do this on your calculator, and again, you'll be absolutely fine. So 7.5 subtract 4, all of that divided by 40, and we get here an acceleration of 0.0875 meters per second squared. So she's not exactly pushing it to go any faster. Very small acceleration, that. But hey, that's what we get, and that's the solution. So let's have a look now at a slightly more involved worked example 2. So this time we have a particle, and it's moving in a straight line from point A to point B with constant deceleration of 1.5 meters per second squared. The velocity of a particle at A is 8 meters per second, and the velocity of a particle at B is 2 meters per second. So now this is completely optional. This is a bit more complex. It's not the most complex, but it's a bit more complex. So what's happening here is we have this particle. It started at A, it's moved to B, but it's slowing down. And so at A, it was going at 8 meters per second. At B, it's only going at 2 meters per second. So it's definitely slowing down. Now, one thing we can do here, deceleration means it's accelerating in the opposite direction to the motion. Acceleration is where it's in the same direction as motion. Deceleration means the acceleration is acting against the direction of the motion. So what I'm going to do here is actually put in a double-headed arrow labelled 1.5 meters per second. Just to denote that actually what's happened is it's slowing down, and it's eventually, if it keeps slowing down, it will stop and eventually turn back on itself. Anyway, the main word here is it's constant deceleration, so we can still use the couple of formulas we worked out before. So just to remind you, once again, the two formulas are A equals V minus U over T, and S equals a half U plus V T. So again, we're going to be reliant on those for this question too. So we can now get started. So A, the time taken for the particle to move from A to B. So let's label on what we know. So we know the deceleration is 1.5. Okay, so we know A. So because the deceleration is acting opposite to the motion, always I would assume, okay, have the direction of initial motion as the positive direction. Okay, so have this as the positive direction. So therefore, because the deceleration is acting against that, we can say the acceleration is minus 1.5. Just be careful with the signs in questions like this. Now we need to work out the other bits as well of what we're told. So the velocity at A, the starting velocity is 8. Whoops, that's V, my mistake. Starting velocity is U, initial velocity. And the velocity at B is 2, so it ends up at B, the final velocity at B is 2. Now we want to find the time, and so based on what we've coloured in, which formula has more information added into it? As you can see here, this one's got 3 colours, the bottom one only has 2, and so we're going to use the top formula, which we can then rearrange. So for part A, if we rearrange A equals V minus U over T, then we get that T equals V minus U over A, just by multiplying both sides by T and then afterwards dividing by A. And so that's going to be V, which is 2, minus U, which is 8, all divided by A, which is negative 1.5. So again, if you wish, you can highlight using a highlighter these bits and pieces. So that's what I'm going to choose to do. So the acceleration is minus 1.5, and the final velocity at B is 2. So final velocity V is 2. So type into your calculator, or otherwise what you should find is it comes out at 4 seconds. And part B, calculate the distance from A to B. Now the distance, now we worked out the time, okay, we can now use this 4 seconds here in this equation for the distance S. So the displacement will be the same as the distance, because at this point here, nothing complicated has happened yet. So S equals half U plus V, so the starting velocity was 8, final velocity is 2, multiplied by the time, which is 4 seconds. So if we work this out now, what we're going to get is 20 meters. Half of 4 is 2, then 2 times what's in the brackets, which is 10. 2 times 10 is 20. I'm being slightly foolish there. I should have used a calculator, because a calculator is the safest way, but that wasn't too bad just to do mentally. We're now given a bit more information. So it says after reaching B, the particle continues to move along the straight line with constant deceleration of 1.5 meters per second. The particle is at point C 6 seconds after passing through the point A. So it says now find the velocity of the particle at C. So nothing much has changed apart from the time itself. So here, the time now, it's 6 seconds after passing through the point A. And we want to find the velocity at C. So if I just take C here and rearrange this. So A equals V minus U over T. So if I multiply both sides by a T, I get that AT equals V minus U. Add U to both sides. Now this is possibly a more common version of the first formula we derived. V equals U plus AT. So this is the rearranged form of the first equation we're going to use. So we're given it 6 seconds now after passing through point A. So it's still relative to point A where it started. And so here, I'm still going to take U as the initial speed, the initial velocity at point A. So at point A, it was 8 meters per second. Now the acceleration, it's still saying it's a deceleration of 1.5, so the acceleration is still minus 1.5. And this time, we're going to multiply by the time. It wasn't 4, like for parts A and B. This is a couple of seconds more than that. It's 6 seconds. So now, the time, I'm going to go for 6, because it's 6 seconds after. So if we calculate this one, we have 8 plus, and brackets, minus 1.5 times 6. We get minus 1 meters per second. So what's happening here is actually the particle has just changed direction very, very shortly before this, and now is coming back towards A. It's decelerated enough so that it stopped for an instant and then started reversing. So now for part D, we need to work out the distance from A to C. So for distance from A to C, we can still use this formula here. So from A to C, if it stops at C after 6 seconds, well, not stops, but we're thinking about C as the end point where we're interested in the motion, we can use the distance from A to C. That's a measure of where it started from to where it is when we've stopped caring about the motion. This is the displacement. The distance from A to C, that means the displacement. So we can use this formula here for S, where S means displacement. So S equals a half, brackets, U plus V times T. So the initial velocity, like we said, was 8. We just calculated the final velocity. At C, it's minus 1, which means it's going back towards A. And the time for that motion was 6 seconds. So again, if we work this out, half of 6 is 3. In the brackets, we're going to have 7. So 3 multiplied by 7, that's going to be 21 meters. So a slightly harder example, I'm sure you'll agree, but not so bad as long as you just take care and picture what's happening and label diagrams and information of the question carefully and accurately. Finally, we've got worked example 3. So a car's moving from traffic lights along a straight road with constant acceleration. Again, that keyword, constant acceleration. So the car starts from rest at the traffic lights, and 30 seconds later the car passes a speed trap. That's essentially a speed camera to many other people. So it passes a camera where it's registered at travelling at 45 kilometers per hour. So we need to find the acceleration of the car, but be careful, it's in meters per second squared. So we need to find the acceleration of the car, but it needs to be in meters per second squared, not in kilometers per hour. So next what we need to do is to find how to change the units correctly. So let's just write down first of all what we do know and highlight it accordingly. So it starts from rest. So because of that, we can say that u equals 0. The initial velocity is 0. 30 seconds later, so the time is 30. It passes the speed trap, that's registered at 45 kilometers per hour. So that's our v, that's a final velocity. So we know t, u and v. We want to find the acceleration. So if you remember from before, acceleration is v minus u all over t. So we can plug in what we know. And so v is 45, u is 0 because it starts from 0, and t is 30. It takes 30 seconds to make this journey to the speed trap. So just filling in what we know here. So u is 0, v is 45. So just type into your calculator, or otherwise you should find that this comes out at 1.5 kilometers per hour. So now we need to start converting it. Sorry, kilometers per hour, I mean to say. So this is kilometers per hour to the minus 2. Now, let's change it unit to unit. So in terms of changing it to meters per second squared, first I'm going to change kilometers to meters. So we need to recall that 1 kilometer is 1,000 meters. So to change from kilometers to meters, we need to multiply by 1,000. Okay, so we can times by 1,000. And so we get that that's 1,500 meters per hour. But then, of course, we don't want it in per hour, we want it in per second. So now we need to think about, well, how many seconds makes an hour? So 1 hour is 60 minutes, and each minute is 60 seconds. So it's 60 times 60, which is 3,600 seconds. So the final thing we need to do is now to divide by 3,600. So if we did 1,500 divided by 3,600 and simplified it down, we could leave it as a fraction, but what I'd suggest doing would be to give it as a decimal. Speeds, distances and times are often given in decimal form. So 1,500 divided by 3,600, we get here 5/12 as an exact fraction, or as an approximate decimal, we get 0.417 to 3 different figures. So equals 0.417 meters per second squared. And that's to 3 significant figures. So I'll just write that in as well. We can have a think about tackling part B. So I'll just section off part A, a little box here, so you can have a look at part B. So for B, we want to work out the distance between the traffic lights and the speed trap in meters. So we can use the formula S equals half U plus V T. And what I'm going to suggest we do first of all is to use the initial units. So U is 0. V I'm going to keep in terms of kilometers per hour, 45. And to make the time consistent, units, because this is in kilometers per hour, I'm going to write the time in hours as well. So 30 seconds is the same as 30 3,600ths of an hour, because like we mentioned before, 1 hour is 3,600 seconds. So if we work this out on the calculator and see what we get, so 1/2 brackets 0 if you want to put 0 plus 45 multiplied by 30 over 3,600. We get 3/16. Now, because I left this in kilometers per hour, the answer for displacement is going to be in kilometers. Now, obviously, because we want it in meters, what we need to do here is to multiply by 1,000, because there's 1,000 meters in each kilometer. So finally, if we take this number here, multiply by 1,000, we get 187.5 meters, and that's the final answer. If you wanted to, you could round it to 188 meters to 3 significant figures, but I think we can treat ourselves with going one more significant figure, especially because this is an exact answer. So I think 187.5 is also acceptable. It's now over to you lot to have a go at some on your own. So if you turn to page 140 and 141, exercise 9C of the Stats and Mechanics book, the last half or half thereabouts of the exercise, from question 7 through to question 13. So try those independently, check your answers as you go. If you get stuck, you know the drill, either ask a neighbour or ask me if that's not coming up to much good. If I'm not around, drop me an email or even leave a comment in the comments section of the video. So thanks again for watching and paying attention, it is appreciated. Please consider subscribing, take care, and I'll hope to see you all very soon. Bye for now.